Aloha BIOCHEM 141. In this video we cover Chapter 1 material, the states of matter, and also physical changes in physical properties. Welcome back. You can see our chapter outline in our textbook right here. In this video we go through section 1.2, the states of matter, and we also discuss physical properties and physical changes. Let's jump over to the notes. Recall from our previous lecture that we divided matter into two categories. It's either naturally occurring or it's synthetic. It's made without the help of man or with the help of man. All of the material around us can be placed in one of those two categories. Well, in today's lecture, we discuss a second method for categorizing matter by its texture. These are the three states or phases of matter. All matter can be placed into one of these three categories: solids, liquids, and gases. You've probably heard of these. They are very different from one another, and these properties here on the left will help distinguish them. Solids have a fixed shape. They are rigid. Their shape doesn't change. Liquids and gases, on the other hand, do change their shape. In fact, liquids will take on the shape of the bottom of their container, whereas gases will expand to fill their container. The volume. Solids have a fixed volume. It's pretty difficult to compress a solid, or at least most solids, into a smaller volume or stretch it apart. So their volume is fixed. Liquids as well. It's very difficult to compress a liquid into a smaller volume. So they both have a fixed amount of volume that they occupy. Gases, on the other hand, it's very easy to compress them. You can take a sample of gas and squeeze it into a much smaller volume or let it expand into a much larger volume. Density, we'll discuss this towards the end of the chapter, but for now, think of density as almost the same as weight. It's basically a description of the weight of a substance relative to its size. And the way you could get a handle on density for now, imagine a chunk of solid material about this size, a chunk of liquid material the same size, and a chunk of gaseous material the same size. So you have all three phases represented here. They're all the same size. Well, the solid and the liquid ones would be much heavier than the gas. See, we say that solids and liquids are denser than gases. They are much heavier than gas when you're comparing them, same size samples. Okay, of course it's possible to have a gaseous material weigh more than solids and liquids. If you have, say, a whole truckload of gas, then it would have more mass, more weight than a tiny morsel of liquid. So gases can be weighed. Now, today we know that everything is made of particles. All matter is composed of particles. It is particulate. So we call these atoms and molecules and ions. And we'll discuss these particles and what they are and much more detail in later chapters. But for now, everything's made of tiny particles. This was not always the idea. People a long time ago, in fact, back in the days of ancient Greece, when philosophers first started to think about matter and material and started to create theories of it, there was a kind of two schools of thought. One of them was matter is particulate. There are tiny pieces of matter. And the other school of thought was that matter is continuous. You could take a chunk of matter, divide it in half, and then take one of those halves, divide it in half as well, and then keep on doing that forever, and you would never get to a smallest piece. But today we know that there are smallest pieces of matter, And we call those atoms and molecules and ions. So eventually, if you keep on cutting a chunk of matter in half, you will get to a smallest piece where if you cut that in half, you would end up with something completely different. Okay, if it's even possible to cut it in half. So anyway, stuff is made of particles, and solids and liquids, the particles are both close together. But solids, the particles are nicely organized. It's a very beautiful organization that you'll see in the particles that make up a solid, whereas liquid particles are very disorganized. In fact, liquid particles are moving around one another, they're flowing, and that's what allows a liquid to change its shape. Solid particles are also vibrating around, but they're not moving relative to one another. They're kind of staying in place. So I'll show you a representation of a solid, a model. This is a model of a chunk of sodium metal. So this would be too small to see. These are the sodium atoms. They're packed together. They're nicely lined up with one another. The order is just about perfect. So we would say that this is a piece of crystalline solid. Most solids are crystalline, where the particles are nicely organized. Okay, solid water is also made of tiny water molecules that are packed together in a nicely organized fashion, and we'll see a picture of that in just a moment. So this would be way too small to see. You just have a few thousand atoms here. You would need the aid of maybe an atomic force microscope or maybe an electron microscope to be able to get an image of this. So this right here is just a simulation, a model. Okay. So solids and liquids, the particles are very close together. Liquids are disordered particles. Gases are much different than solids and liquids in this respect. The particles of a gas are much more far apart than you'll see in the solid and liquid phase. And gas particles are flying around. A lot of disorder here in the gas phase. So the idea of dividing matter into the three states, solids, liquids, and gases, has also been around for quite a long time, about the same amount of time as the idea of the tiny particles. If you go back again to the ancient Greeks, the first person to think about and basically say that matter is divided into these three categories, although he had four categories. His name is Empedocles, and he lived from 494 BC to 434 BC. And perhaps you've heard of the four elements: earth, water, air, and fire. Empedocles said that all of the material around us is made of these four elements. And the reason you would see lots of different types of matter out there, you have a tree, a leaf, a lake, is because the proportions of the elements in each type of material is a little bit different from each other. But substances which were solids, they would be composed mostly of earth, with perhaps a little bit of water and air. Substances that were liquids were primarily made of water, and gases were primarily made of air. So again, there are different types of liquids out there. They're all mostly made of water, but one of them might have a little bit of earth, and another one might have a little bit of air mixed in. So that's what gives you different types of liquids and such. There was a fourth element that Empedocles mentioned called fire, and this was a special element. It helped instigate change among the other three. So fire was a special element that caused substances to change. For instance, if you have some liquid water and you heat it up, it will eventually boil into water vapor. So if you add a little bit of fire, you can convert water to air. Another example would be, suppose you have a tree and you add a little bit of fire, you can burn it up and it'll convert into smoke. Okay, now so the elements can interchange. So there you go. The elements correspond directly with solids and liquids and gases. And even this special element of fire, we have something today that we call energy. And energy helps material change into different types of material. Now, there was a lot more to the ancient Greek elements than just this, and we're just touching the tip of the iceberg. For instance, Aristotle, who came a little bit after Empedocles, added a fifth element called the ether, which was the material that stars and such out in the night sky were made of. They never seemed to change, and so they must have been made of some other special type of material, some ethereal or heavenly material. And so there was a fifth element called the ether, and Aristotle expanded on Empedocles' theory, and the idea of ancient Greek elements continued on for millennia. It didn't really go away until the 1600s. Okay, but it's very interesting that this way of categorizing matter has kind of been around for a long time. Here's an example of a substance in its three phases of matter. Let's take water. We all are familiar with water. The three phases of water, and today we know that water that is made of tiny particles called water molecules. This is the smallest piece of water. If you cut this in half, you would no longer have water. So the smallest piece of water is called the water molecule. And this water molecule has inside of it one oxygen atom connected to two hydrogen atoms in this triangular fashion. All water molecules look like this, and this is the tiniest piece of water, and that's why we represent water as H2O, for the two hydrogens and the one oxygen. So water can exist in all three phases. If you have a chunk of solid water, it has a nice rigid shape. It's not changing its shape. All of the water molecules are compacted in there. And I'll show you a representation of solid water. Here we go. I love Janice Smith's textbook because she, in discussing chemistry and biochemistry, she also gives us some cool pictures of Hawaii. Janice Smith is a professor at Manoa, and so she's familiar with lots of areas in Hawaii. And here's some pictures from the Big Island. So here you see the top of Mauna Kea, the snow on the top of Mauna Kea. This is solid water, snow. And so the water molecules are nicely packed together with a good order, a very, ordered structure of the water molecules. Okay. Now, if you take solid water and you heat it up, you will eventually vaporize it or boil it off into liquid water, and liquid water takes on the shape of its container. Maybe it's just a puddle on the floor. So liquid water, these water particles are still packed together, but much more disorganized. Okay, this is a picture of Akaka Falls, also on the Big Island. Now, if you heat up liquid water, you will eventually boil it off into water vapor. So here's a puff of water vapor, and the particles of water, the water molecules, are very far apart now. Okay, and they're flying around, bouncing into each other and such. And so here's a picture also from the Big Island of lava going into the ocean and causing some of the water to boil off. So this steam right here, if you could see the water molecules, you might see them whizzing around kind of like this with a lot of space between them. Okay, so kind of a cool picture. And one more representation of these changes. So, going from solid, you heat it up and you melt it into liquid, and then You keep on heating it and you boil it into the gas phase. So you should be familiar not only with the 3 phases of matter, solid, liquid, and gas, but the 6 phase changes. So here is a diagram that might help you remember that. Solids can melt into liquids, and liquids can vaporize into gas. If you go back the other direction, gases, when they cool down, they'll recondense, or they'll condense into the liquid phase, and cooling a liquid will freeze it back into the solid phase. It is possible to go between solid and gas directly, and solids can sublime into the gas phase. That's called sublimation. And gases can deposit back into the solid phase. That's deposition. So remember these, the 3 phase changes and the 3 phases and the 6 phase changes. Now, a particular transition between 2 phases can be more it can be represented in more detail with the aid of a chemical equation. If you know the chemical formula for the substance, in this case water is H2O, and you want to represent, say, the melting of water, well, the chemical equation that describes the melting of water, you have the material that you start with on the left. This is your reactant material. So when you're melting water, you're starting with solid water. That would be H2O(S) for solid in parentheses. And the material that you end up with is written on the right of the arrow. This is your product material because you're producing it. And here, when you're melting water, you end up with liquid water, and so it's H2O liquid. So your reactants are always on the left in a chemical equation, and your products are always on the right. Anything above the arrow sign is something that's added to the chemicals to help them change into the products. So in this case, the triangle represents heat. By the way, the melting temperature for water is 0 Celsius or 32 degrees Fahrenheit. We'll talk more about temperature towards the end of the chapter. Now this change right here, this by the way is our first chemical equation, and we'll see many more. This is a rather simple chemical equation because the substance, water, is still there at the end. It's only changed its state. First you have solid water, and then you end up with liquid water, but it's still water. So the substance has not changed its identity. We call this a physical change. A physical change alters a substance without changing its identity. Another example of a physical change is the sublimation of dry ice. Recall, sublimation is when you go from solid directly to the gas phase. That's sublimation. So sublimation of dry ice. Dry ice is a special type of ice. It's not water ice. It's made of carbon dioxide, actually. It looks just like regular ice, but the substance isn't water. It's actually solid carbon dioxide. And solid carbon dioxide, when you just let it sit out in the room, it never melts. It will fizzle away into the atmosphere. It goes from the solid directly to the gas phase. The formula for carbon dioxide is CO2, and that's because the tiniest particle of carbon dioxide, a single molecule of carbon dioxide, has 1 carbon attached to 2 oxygens on either side. So that's what a carbon dioxide molecule looks like, and they all look like that. So the chemical equation representing sublimation of carbon dioxide, you start with CO2 solid, you add a little bit of heat, and you end up with CO2 gas. You should note that physical changes are pretty easily reversed. So going back to the first one, liquid water is easily frozen back into the solid phase if you just cool it down. And same thing with dry ice. gaseous carbon dioxide, if you cool it down in a really cold freezer, it will freeze back into the solid phase. It's very easy to reverse a physical change. The third example is a little bit different type of physical change. This is dissolving salt in water. And when we say salt, we're talking about table salt. There are many other salts out there, but if all you say is salt, you're talking about table salt. So table salt is sodium chloride. That's NaCl. That's the formula for sodium chloride. And I'll show you what sodium chloride kind of looks like. Here's a pile of salt inside of a beaker. And imagine if you have a little submicroscopic pair of tweezers and you were able to take out a tiny, tiny morsel that's too small to see, then and you zoom in on it, you might see something that looks like this. Okay, here's a tiny morsel of sodium chloride, and the particle, this would be too small to see. Just a few thousand atoms here. So here you see the sodium atoms are the smaller pink ones, and they're surrounded by the chlorine atoms are the larger yellow ones. But still, the structure is nicely ordered, very beautiful. It's cubical as well. Sodium chloride, it looks like a pile of salt here, but if you were to zoom in using your molecular magnifying glass, if you had one, you would see that the particles are nicely, perfectly cubical. The atoms, have a good arrangement, very ordered, very packed together. So here's your solid sodium chloride. That's the material that you're starting with. When you dissolve this in water, you add water to it, and what do you end up with? Well, you end up with sodium chloride that's dissolved in water. It's not liquid sodium chloride. What we say now is you have sodium chloride in aqueous solution. The salt is now in aqueous solution. So whenever a substance is dissolved in water, after the formula for the substance, you put in parentheses AQ. We'll be dealing with a lot of aqueous solutions this semester, so I wanted to introduce this early on. Now here, it looks just like water. I've drawn the green dots just to denote that there is something in there, but really a solution of sodium chloride, you cannot tell that there's anything in there. It looks just like water. You can't see the particles in there, unless you dump in like a truckload of salt and there's not, you have too much salt and it doesn't all go into solution. Well, then you might have some solid powder at the bottom and be a little bit cloudy. That's because some of the other stuff didn't quite dissolve. But if you just drop in a little bit of salt into water, it all goes in solution and looks just like clear water. The last thing to discuss in this video, along with physical changes, you should be aware of what the physical properties of a substance are. Physical properties are properties of a substance that can be measured or observed without changing the substance's identity. So if you have a chunk of matter and you want to observe or measure something about it, but you don't want to change it into a different type of matter, like you're not going to burn it, or you're not going to do something crazy which actually changes its identity. We'll talk about such chemical changes in our next video, but imagine you just want to carefully observe a chunk of matter without changing it in any real way. Well, one thing that you can observe or measure is the mass. You can put the chunk of matter on a scale and you can weigh it, and you're not really changing that chunk of matter. You can measure the volume without changing it. You can look at its shape. You can look at its state. Is it solid, liquid, or gas? You can observe its color without it changing. You can observe its odor, if it smells or not. You can look at its melting point. At what temperature does it melt? Okay, water melts at 0 degrees Celsius. Other substances have their own melting point, and you can observe this without the substance changing its identity. You can also observe its boiling temperature, its boiling point, and also whether it dissolves in water, its solubility. So lots of physical properties out there. In our next video, we will discuss chemical changes and how to categorize matter by composition. So stay tuned for that.